Good afternoon. My name is Junghee. I am currently with Korea University, and I am also serving as a chair of the blockchain major in our department. Before starting my talk, I first would like to thank Ripple for supporting our research and also organizing this wonderful event. And also, I would like to thank all of you for coming. But I think you came to this session probably not for my talk, probably for others, because I suppose most of you are not very familiar with hardware concepts like Verilog programming or macro cells, CMOS technology, something like that. So today, instead of delving into the details of hardware implementation, what I'm going to focus is more on the high-level overview of some arithmetic optimization techniques that can be applied to the ZKP proof generation. So first of all, I will begin with some computation kernel in ZKP. And I think I don't need to explain details about ZKP. And yeah, this is the common computation kernels in ZKP protocols. And yeah, there are also many protocols that don't employ MSM nor NTT, but actually I am also working on them. But as long as I know, the MSM-based proof protocols are one of the most popular protocols in this field. So we are currently focusing on the MSM. Here, MSM stands for multi-scalar multiplication. And from our profile, you can see that most of the execution time is actually attributed to MSM, up to 70%. And the second largest computation kernel is NTT or FFT, which corresponds to about 20%. So in this talk, I'm going to focus more on the MSM, how to accelerate MSM. So even though the title includes ZKP, so actually what I'm going to talk about is accelerating MSM. So if I disappoint you, I apologize. But you know, the most heavy computation kernel is identified as MSM. So why it takes so long time to perform the MSM? You can see this equation that what we want to do is multiplying a point with a scalar and summing them up. But here, addition and multiplication are not what we know. It is point addition and point multiplication on elliptic curve. So it's very complex computation kernel. I will show you in a minute. And also, we have to deal with a large integer, which is up to 768 bits, which is big. And also, we need to multiply and summing up to 2 to 23 numbers. So it's also very big number. So that's why it takes so long time to compute the MSM. So that's why I am currently working on how to accelerate this MSM computation kernel. Bell person? Yeah, actually, this result came from my students. So frankly, I'm not sure. So yeah, I thought that it is one of these ZKP protocols. I know that you are an expert in this field, but I am not. I am more focused on the hardware implementation. And anyways, thank you for your question. Okay, so what we want to implement in hardware is the multi-scalar multiplication, which can be composed with point addition and multiplication, which is actually implemented by modular multiplication. And all of the hardware implementation is based on adders. So I'm going to explain each levels from the bottom to the top, how we implement these computation kernels in hardware. Okay. So this is very typical adder implemented in hardware, which is called carry look ahead adder. And this is very basic adder, but there are many derivatives. Yeah, because when we design some circuits, we have to consider not only performance, but also hardware cost and also power consumption, that kind of many metric. So yeah, depending on which metric we want to improve, yeah, we can come up with these many types of adders. And when we implement the modular multiplication, there are a couple of existing optimization techniques. One of the popular one is the Montgomery algorithm, which is shown in this slide. The key idea of this algorithm is that instead of using an expensive division operations, we can replace them with some cheap operations like this, just addition or yeah, just divide by 2. Because when we implement division by 2 in hardware, then we can implement it just shift operator. So it is much cheaper than just general division operation. And we can also save time to pre-compute a constant, so which doesn't depend on the primary inputs. And this is the point addition on elliptic curve. You can see that we have some expensive operators like division and also multiplication. So instead of doing the division operation, every time we work on the points, we can actually change the coordinate system. So there are some known different types of coordinate systems. Typically, we are using this one or affine, but we can introduce another dimension, then we can reduce the number of division operations. For example, if we introduce z, then instead of x and y, we can use x by z, y over z. Then when we just convert this coordinate system only once, then all the following operations can be done on this coordinate system, which doesn't require the expensive division operation. So this is one example on BLS 12 yeah, curve. And yeah, this is what actually we do. So yeah, compared to this equation, instead of division operator, we can see that the division operation is completely removed from these equations. So when we start the multiplication, we can change the coordinate system once and do all the computations 2 to 23 to 2 to 20 or 2 to 30 times, and then final result can be converted again just once. So it's much efficient implementation. But the thing is, there are very small probability that we cannot convert this coordination system. So there is very small possibility of some exception. And then, based on these primitive kernels, we finally can implement the multiscalar multiplication. And because we are dealing with very big numbers, typically this bucket method is being used. So instead of, so what we are supposed to do is multiplying scalar with point and then summing up them. But if we change the order of operation, we can save some time. So instead of multiplication, we begin with addition first. And then if some points are multiplied by the same scalar, then we can do the addition first and then followed by multiplication. In this way, we can reduce the total execution time. So this slide shows the key ideas of the Pippen's algorithm, which is also called bucket method. So these are some known hardware accelerators. The first one is PipeZK, and which is implemented in ASIC, and it supports 3 kinds of electric curves. And it employs 72 point addition pipeline. So the point addition logic, the circuit, is the biggest hardware in this accelerator. And the reason is that because when we implement this many operations for one point addition, you can expect that it becomes big. And because we want to boost the performance as much as possible, typically we are employing some pipelining techniques. So if we employ pipelining in hardware, typically the hardware cost increase, but the parallelism also increase, so that we can increase, so that we can boost the performance. And this PipeZK only supports up to 2 to 20 points, and it takes about 2 seconds to do the point addition, MSM basically. And these also 3 existing techniques are implemented in FPGA, and they support the same curve, and they have some different implementation of the point addition. And the last 2 hardware accelerators supports up to 2 to 26 numbers. And the last one, the hard camel, is the probably, to my best knowledge, the fastest one so far. And this is the winner of the last year Z Prize competition. And this is the architecture, the hardware architecture of this one. And this one. And this is what our research group is currently working on. In the Pippen's algorithm, the computation takes steps of accumulation and aggregation for multiple windows. And our key idea is doing the accumulation and aggregation at the same time. The main reason is that when we perform aggregation, it's data, because of data dependency, we cannot fully utilize the hardware resources. So instead of doing them separately, if we do them concurrently, then we expect that we can improve the performance a little bit more. And in the previous hard camera architecture, actually the aggregation is done in software. But we are going to implement the aggregation in the hardware so that we can reduce the overhead of data movement as well. And because the bucket method, the name implies that we are using some number of buckets. And buckets here mean that we need to store some intermediate results in the memory. So if we employ a large number of windows, then we need the corresponding number of buckets. But if we parallelize the aggregation and accumulation, I am expecting that we can reduce the size of the on-chip memory. So that's the another one. Simply speaking, we are seeking for a technique that reduce the execution time, but at the same time also reduce the memory size. So that's what we are currently working on. And I was hoping to show you some experimental results, but unfortunately, we got some results. Yeah, but we need some more time to verify that those results are really correct. So yeah, sooner or later, yeah, we plan to publish this technique as a research paper. Okay, so this is the summary of what I just yeah, gave you the overview of the hardware acceleration of the ZKP protocol. So MSM is one of the most intensive computation kernel in the state of the-art cryptographic algorithms, and it consists of we have to implement the multiscalar multiplication by modular multiplication and some basic adders. So there are some known hardware accelerators, and also we are also working on some improving the performance of the existing accelerators. Okay, yeah, thank you for your attention, and yeah.